All right. So thanks for attending, everybody. We're super happy to have Brantly Callaway here today, and he's an assistant professor at the econ department at the University of Georgia, and he's going to be presenting uh, this new working paper, "Difference in Differences with Continuous Treatment," that's joint work with Andrew Goodman-Bacon and Pedro Santana. And questions are welcome throughout. So thank you very much, Brant, for being here, and pass it over to you.
Okay. Can you see those slides okay? Okay. Good. Okay. Well, thank you all for having me. Thanks, Taylor. I've really been looking forward to this. I think it's a very good thing that people have been having these get-togethers and reading what I think are a lot of interesting papers this summer. The paper today is basically brand new, so it's been out maybe right at a month, I think. And this is co-authored work with two people I think a lot of you will know. So Andrew Goodman-Bacon and Pedro Santana, who both presented in the reading group earlier in the summer. And the paper is going to be about differences with continuous treatment. So I was thinking about how to start, and I guess as evidenced by having a DID reading group, there's been a lot of recent interest in differences methods, and probably where I came up with to start was just to kind of start by getting everybody on the same page. This will be probably review for people who've been coming to this throughout the summer, and maybe just to for those who haven't, to kind of frame where the literature's been in the last been moving in the last year or two. And I think I'll start by probably painting with too broad of strokes here, but I think you can think of a lot of these recent papers as being more or less in one of two categories. One category has been, and kind of the first wave of papers have been about diagnosing issues with two-way fixed effects regression. So these are the regressions that have been for many years have been the way that researchers have implemented differences. But a number of papers diagnosing issues with those sorts of regressions in terms of implementing DID. And if I can summarize those papers in maybe 2 bullet points, I think the key things that they point out is that two-way fixed effects regressions can go wrong or perform poorly in cases that do show up quite often in applications. One main issue is that already treated groups that have already been already started participating in the treatment, they sometimes serve as the comparison group or as the control group for groups that become treated. And what this leads to is that if there are treatment effect dynamics, so if the effect participating in the treatment can vary across time periods or vary with length of exposure to the treatment, which differences, so the main assumption in differences is about parallel trends. Parallel trends assumptions are about untreated potential outcomes. They have nothing to say about treatment effect dynamics. And so if you have these treatment effect dynamics that aren't ruled out by the assumptions that you probably have in mind that you're making, you can get very poor estimates of treatment effect parameters. And here I say very poor, but this is the sort of thing that can lead to what's been called in the literature, often emphasized in the literature, of negative weight. So if you think of two-way fixed effects regressions as being weighted averages of some underlying treatment effect parameters, if you have treatment effect dynamics, it can lead to negative weights. Negative weights can be a big problem. I mean, if you're willing to push on this, you can easily write down examples where something like the effect participating in the treatment is positive for everyone, but due to the estimation method, due to using a two-way fixed effects regression, you could somehow estimate a negative effect participating in the treatment. Now, I don't think that's the usual case, but you do open yourself up to those sort of issues, and I think I don't think it would be uncommon for a less extreme version of that issue to be reflected in the two-way fixed effects estimates that you get. And then the second issue that this literature has pointed out is that with a two-way fixed effects regression, the weights on these underlying treatment effect parameters, they're driven by the estimation method. And so if you think about like a regression, like the weights, they're coming from something like if the effect is homogeneous and that you want to maybe under some extra conditions like some kind of homoscedasticity or something, you want to get efficient estimators. Those are where the weights are coming from. But in the presence of treatment effect heterogeneity, the weights themselves are a bigger issue, and the weights are being driven by the estimation method may have undesirable properties. You may put more weight on certain parameters than on the parameters that you'd like to. And so the second strand of the literature here, which also includes pretty much all the papers that I put in the first strand, have proposed a number of fixes to these kind of issues. This includes my paper with Pedro, who I think I saw is in the audience here. But basically, if you think about the idea, the common strand of all these papers is the idea of explicitly making the good comparisons. So make the comparisons that you like that show up in two-way fixed effects, and just don't make the bad comparisons. Don't use already treated groups as a comparison group. And if you kind of, basically, at least in our case, as soon as you moved out of a framework where you had to estimate a regression, it was pretty easy to see how to do this. That you just pick up the things that you like, don't make the comparisons that you don't want to like. And so that fully addresses this negative weight sort of issue, this issue coming from treatment effect dynamics. And then the second issue about weights being driven by the estimation method, you can address this by just choosing your own weights. Don't have the estimation method choose the weights, you choose the weights. And if you do that, you can choose weights that target an overall average treatment effect parameter. You can choose weights that target an event study parameter. So event study being like that you're interested in how the effect of the treatment varies with length of exposure to the treatment. Those are just to choose a different set of weights. Or you could be interested in other things, and you can just pick weights that correspond to the thing that you want to go after. And so one of the things that, with just a couple of exceptions, those papers have focused on has been the case with a binary staggered treatment. So binary treatment means that either individuals participate in the treatment or they don't participate in the treatment. And staggered treatment means that once you become treated, you stay treated. So we're still allowing for variation in treatment timing. So my treatment timing could be different from your treatment timing, but once we become treated, we both stay treated after that. In my view, this is the leading case. But that being said, I think there's still a number of other important cases corresponding to more general treatment regimes, and that's what the paper today is going to be about. And just to motivate more that perhaps there's demand for this, one of my co-authors came up with this Twitter collage here of people being interested in differences with heterogeneous treatment effects, but with a continuous treatment. And so that's what we're going to do in the current paper. We're going to think about kind of similar sorts of things as the previous literature. So you notice, so this paper has Bacon, it has me, and it has Pedro. So we're going to do the whole thing in this paper. We're going to have kind of a diagnosis of some issues, and we're going to try to propose at least some partial fixes. Our fixes are actually not going to be as good as they are in the binary treatment case. We're not going to be able to fix everything or as much as we did previously, but we'll give some ideas there. And so just to kind of be a little bit more clear about what we're going for here, is we're basically thinking about a case where traditionally a researcher would have estimated this kind of two-way fixed effects model. I'm not sure. If I point to something with my mouse, can you see that? Yes. Okay. So this is an outcome. You have a time fixed effect. You have an individual fixed effect. Beta would be the parameter that would be reported in an application. D is the amount of treatment. So here it could be more general treatment regimes means that this can take more values than just 0 and 1. And this is going to be a dummy variable for whether or not you're treated in a unit is treated in a particular time period. And then we just have these kind of idiosyncratic time varying unobservables. We're going to think about the case where where the treatment is probably continuous enough that a researcher would estimate this sort of model instead of one that maybe includes a sequence of dummy variables. But we're going to think about this in a world with heterogeneous treatment effects, basically. And besides that, so in practice, I think researchers typically interpret beta maybe somewhat loosely, but as with the idea of being a causal response. So is an effect of what's the causal effect of a marginal increase, a small increase in the dose on outcomes. And so in the presence of treatment effect heterogeneity, the causal effect of a marginal increase in the dose, it could differ based on the dose. So like if you have a low dose, the effect of a little bit more dose could be low or high. If you have a middle dose, it could be different from that. It could be low or high itself. And if you have a high dose, it could be different again. And so in the presence of heterogeneous effects like that, I guess we would hope if you estimate this kind of regression that beta is going to correspond to some kind of weighted average, hopefully, of those causal responses. We'll see kind of as we go along if that's going to be the case or what conditions you need to invoke in order for something like that to hold. And then so I think I have a couple slides here just to kind of give you the summary of the paper, the high level summary of the paper before we kind of dig into the main issues. And so what we're going to show in the paper is first we're going to show that a lot of the issues that show up in the case of the binary treatment, especially with regards to two-way fixed effects, they continue to show up in the case when you have a more complicated treatment regime, when you have multi-valued or a continuous treatment regime. And this is probably not surprising, but this first issue that already treated units serve as a comparison group, this continues to show up, and this can lead to the same kind of negative weights as before and can potentially lead to maybe very poor estimates of kind of an average causal effect parameter. Second, just like before, the two-way fixed effects, the beta from the two-way fixed effects regression is going to correspond to a weighted average of underlying treatment effect parameters. And again, the weights are going to be driven by the estimation method. So this will mean things like the weights are going to be sensitive to maybe some things that seem to be good, like the size of different groups, but will also be sensitive to the average amount of dose in a particular group. Will also be sensitive to treatment timing, like is a group treated early, middle, late, things like that. And especially the last one doesn't seem to be really a desirable thing. And then one more thing here is, and I'll explain this probably more precisely as we go along, but there's one more source of issues with two-way fixed effects regressions, and that's that if they're heterogeneous causal effects, so heterogeneous effects of dose, so within the same time period, but across groups where a group is based on timing, that can be another source of negative weights in the two-way fixed effects regression. Just like in the case with the binary treatment, though, we can fix all of these issues. And the way we fix them is the same strategy as before, is carefully make the comparisons that you want. So don't just explicitly don't use already treated groups as a comparison group. And by choosing our own weights, choose weights that target, say, an overall treatment effect parameter, or choose weights that target an event study, something like that. That will fix all of these problems. So this is the positive slide. We're about to flip to the negative slide. The negative slide is that there are new, I think, fundamental and conceptual issues in the case with a multi-valued treatment, a multi-valued or continuous treatment, that just don't show up in the case when you have a binary treatment. And these issues come from either explicitly or implicitly when you try to compare treatment effect parameters across different doses. So trying to compare the treatment effect of, say, a low dose to the treatment effect of a high dose. And the intuition for this is going to be that if you think about standard versions of difference and differences, standard parallel trends assumptions, these deliver ATT type parameters, ATT average treatment effect on the treated type parameters. And the treatment effect on the treated parameters, they're local parameters in the sense that they're specific to a particular dose. So if you do something like standard, what I'll call in a minute, standard difference and differences, you're going to be able to identify effects that are local to a specific value of the dose. But when you try to make comparisons across different values of the dose, these comparisons, they're going to include both a causal effect of more dose. So like if you see an ATT for a low dose and ATT for a high dose, and you compare them to each other, part of the difference can be due to the causal effect of getting more dose, but another part of the effect could be it could come from a selection bias term, just that there are kind of fundamental differences between units that have more dose relative to less dose that aren't ruled out by parallel trends assumptions. And we'll see that this, I think, turns out to be an important issue just from an identification standpoint, and then also when you think about relating these sort of arguments to two-way fixed effects estimators. If you want to get rid of these selection bias terms, these are the second ones here. These selection bias terms are undesirable terms to show up in your estimator. If you want to get rid of these, it's going to require stronger assumptions than researchers have typically made when they think about difference and differences. And I think these assumptions are likely to be substantially stronger in practice. And unlike the last slide, there aren't easy fixes here. So there's not, we don't have any kind of clever trick in the paper to get around this issue. And my sense is that there just does not exist a clever trick to get around this. And so at least in some sense, this is my reason for saying that this is kind of more negative than the earlier literature on the case with the binary treatment. There's not, at least what we're going to talk about, there's not kind of just move to a better estimation procedure and fix everything. This is going to kind of say that you probably need to invoke stronger assumptions, and you need to think very carefully about if those assumptions are justified or not. Okay, and then so I'm about to jump into kind of the main part of the paper, start to get into some of the details. Before we do that, I think I said at the beginning, this is a brand new paper, so you may notice some parts that are a little bit rough around the edges. This is the first time that I've presented it. I think this is the first time that any of us have presented this. So if anything's confusing, please feel free to jump in. I tried to practice beforehand so that my explanations would be clear, but I'm not sure that will always be the case. You'll also notice the paper's not 100% complete. We don't have an application in the paper, which I think would be helpful to kind of help wrap your mind around what we're saying here. We also don't have any code that you can go download. In some sense, we will provide code at some point, probably in the not too distant future. In some ways, I don't know that this is so much a code paper per se, but maybe somewhat more of a conceptual paper. Anyway, all that being said, we certainly welcome comments and suggestions now, or I'm happy to stick around after and talk in a lot more detail. I think also on the last slide, I think I have my contact information that if you'd rather reach out that way, I would be happy to talk in more detail there.
Right, there's just a question in the chat. I'll just announce it for you. I know it's hard to keep track of the chat as you're presenting. So
oh yeah, thank you.
Ryan is asking, is this last issue on the BLAD slide something specific to the staggered case or for any application of DID with continuous treatment?
Oh, it's going to be any application. So the first thing that we're going to come to even this is a very good segue for for my next slide here. Is so we'll start out by talking about kind of like the textbook version of differences. This is the easiest. So the first thing we'll talk about, and actually probably the thing that I'll spend the majority of our time on, is a baseline case, this textbook case where there are 2 time periods, where no one's treated in the first time period, where there's an untreated group that isn't treated in either period. And so all that's different from kind of like, say, mostly harmless econometrics is that in the second time period, treated individuals can be treated with a different dose. And we'll see, yeah, these same issues are going to pop up in that case. So it's not just going to be a staggered adoption sort of issue. After that, so just Taylor, I'm not able to see the chat for some reason, but if you see,
let me see here.
oh, here we go. Sorry, I think I got it now. John, let me, so for the second question, if you'll just let me defer a little bit, I'll be more precise about what selection bias actually means and how it's related to parallel trends. So this is coming in the next few slides. If you still have questions, just put another message there and I'll speak, try to be clear, but I should answer that question over the next few slides. Thanks. Okay, so besides that, after that, we'll talk about two-way fixed effects in this sort of same baseline case, and then we'll move to more general cases with multiple periods and variation in treatment time. In some ways, actually, once we cover the first 2 sections, the third and fourth section is kind of notationally more cumbersome, but will reflect a lot that's going on from the first 2. Was there? I think somebody raised their hand.
Yeah, hi. I had a question, if I could ask.
Please.
I hope you can hear me.
Yeah, I can hear you.
So this is more about the introduction. So I was thinking about the example we gave in the introduction about smoking causes cancer. So would this be applicable to this sort of a research question? Because if you only observe smoking or the number of packets of smoke a person consumes from the first time period he's recorded, so you would never have a pre-period where he's never smoked before. So would it be difficult in that case?
Actually, so this is an interesting question. So I won't spend very much time on this issue today, but having a multi-value treatment does give you some scope for recovering treatment effect parameters, even when you don't have an untreated group or a group that doesn't participate in the treatment over and over again. Under some kind of parallel trends assumptions, you can compare people whose changes in the dose, potentially compare people whose changes in the dose who experience relatively different changes in the dose. So I think there's some promise for being able to exploit this kind of setup to answer that sort of question.
Thank you.
Sure. Okay, I think I will keep going here. Whoops. Okay. All right. So I tried to make the slides not too mathy here, but I'm not 100% sure that I was successful at that. So let me tell you the kind of notation that I'll use, at least for this part of the talk. I'll use potential outcomes notation. We're going to have 2 time periods. I'm going to call them period T and T-1. In the first time period, no one's going to be treated yet. And in the second time period, some units are going to become treated, some are going to remain untreated. Among those units that become treated, they can experience different amounts of dose. We can think about potential outcomes in this case. So this YIT of D, this is unit I's outcome in time period T. If they were to experience dose D, this allows us to think counterfactually, to think what a unit's outcome would be if they experienced a different amount of the dose. And then in terms of observed outcomes, so again, in the first time period, because no one's treated yet, in this section, we'll say that we observe untreated potential outcomes for everyone. And then in the second time period, the observed outcome is the potential outcome corresponding to the dose that a unit actually experienced. So if you have a high dose, the outcome that we observe for you is a potential outcome corresponding to that high dose. Okay, the next thing I want to talk about is what parameters you could be interested in identifying here. This is a little bit more complicated than the case with the binary treatment because there are more parameters that you could potentially be interested in learning about. We kind of categorize these a bit. The first one I'll start with is what we call in the paper level effects, or I'll probably also call this average treatment effect on the treated. This is essentially analogous to the ATT in the binary treatment case. If you back up one second, even if you think about difference and differences, like textbook difference and differences with 2 time periods, the target parameter there with a binary treatment is the average treatment effect on the treated. And so this thing is kind of the natural way to generalize that. And just to read this to you, it's a difference between potential outcomes under dose D relative to untreated potential outcomes. It's on average, and it's specific to those who actually experience this dose. So if you take, the reason we double index this here is so that you could imagine different sorts of, this D doesn't have to be equal to this D. So it could let you think about what would the effect of a high dose be relative to no dose, but for people who actually experience a low dose. But the thing that's going to be identified is the one that's the effect of a particular dose relative to no dose, relative to being untreated for people who experience that dose. Okay, and then the main other sort of parameter that you could be interested in the case with a multivalued or continuous treatment is what we call a slope effect. Sometimes in the literature, these are called average causal responses. And what this is, we call this ACRT for average causal response on the treated. And it's how much, so if you take those who actually experience dose D, it's how much their outcomes would increase under a marginal increase in the dose. So if they got a little bit more dose. This, you can think about this like both of these first two, they're indexed by dose. So you can imagine thinking about these functionally. So like if you knew what these things were, you might plot them. You might see either what is ATT, so what's ATT as a function of the dose. You might see what the average causal response is a function of the dose. Two-way fixed effects, it reports one number that you would hope would somehow aggregate maybe some parameter like this. If you want to turn this into just one number, you can average over all of these. So in a world with heterogeneous effects, again, maybe some of these causal responses, maybe they're small for some values of the dose, maybe they're big for other values of the dose. This thing would just be one number that averages these together. Also, so I'll mostly talk about the case with a continuous dose, but if you're interested in the case with a discrete dose, if you're interested in a level effect, it's exactly the same as with a continuous dose. If you're interested in a slope effect or an average causal response, those derivatives in the previous slide aren't available, but you can think about average causal responses that are the effect of moving to the from one dose to the next biggest dose among those who are while holding the group that experienced one dose constant. Okay, I'm gonna, well, let me just mention this. Oh, Melanie, I see your question here. Yeah, this is a very good point. So going back to the earlier question, if you have no untreated group, it doesn't seem like you could identify a level effect, but you could potentially identify a slope effect. Yeah, that's a very good comment. And then one other thing, just mainly is a side comment here, is that I usually think in the binary treatment case, I usually think of ATT as being like a level effect. But in the binary case, it's also a causal response. So ATT in the case with a binary treatment, so it's equal to this. It's ATT of 1, 1, but it's also equal to the average causal response on the treated 1, 1. You can either think of it as a level effect, or you can think of it as the effect of going from no dose to dose being equal to 1 among those who have dose equal to 1, which means being treated in the case of the binary treatment. So that's not a super important point, but it kind of helps unify some of the results that we'll show later. Okay, so now that we have some parameters that we would be interested in identifying, let's talk about how to identify them in a difference in differences setup. If you're used to difference in differences with a binary treatment, this is going to be the analogous assumption for this, for the case with a multi-valued or continuous treatment, what I'm going to call, in quotation marks, standard parallel trends. And this says that for any value of the dose, that this is the path of untreated potential outcomes. So on average, the path of untreated potential outcomes among those who experience dose D is equal to the path of untreated potential outcomes among the untreated group. This sort of thing is potentially helpful because we don't see this path of untreated potential outcomes for those who experience some dose, say who have a high dose or low dose, but we do see the path of untreated potential outcomes for the untreated group. And I'm just going to quickly step through how this kind of parallel trends assumption, you could use it to identify the average treatment effect on the treated, even when you have a multi-valued or continuous dose. The arguments are going to be essentially identical to the case with the binary treatment. But anyway, so here's the average treatment effect on the treated, specific to dose D. And this is just the definition of it, the difference between potential outcomes under dose D relative to untreated potential outcomes specific to those who experience this dose. Like in the case, like the argument would go if you had a binary treatment, if you add and subtract this term, so this is average untreated potential outcomes in the first time period among those who experience dose D. So you subtract it here, so there's a minus, you add it back here. This second term, this is where you can employ the parallel trends assumption. So this thing is equal to this, employ parallel trends here, you get this. And now if you look closely at this, you'll see that everything's identified here. So among those that experience dose D, the potential outcomes that we see in the second time period is the potential outcomes corresponding to that dose. In the first time period, because they're not treated, it's untreated potential outcomes. So that means this term is identified. And this thing is the path of untreated potential outcomes for the untreated group. And those are the outcomes that we see for the untreated group. So we can replace all the potential outcomes with observed outcomes and say that the average treatment effect on the treated for those that experience dose D is equal to the average change in outcomes that those that experience dose D actually experience relative to the change in outcomes that the untreated group experienced. And you can think, so this is the actual change that happened among those that experienced dose D. Under parallel trends, this is how their outcomes would have evolved over time if they had not been treated. And so that's how you recover the ATT. And in some sense, this is exactly what you would expect here. This looks just like the 2-period case. In fact, if you're, it seems to me that if you're going to do any kind of difference in differences, that this is the sort of quantity that you're going to get that's going to come out of the data. Before I switch to that side, to the next slide, perhaps it looks like we're done. If you look down here, the slide counter, it says 14 out of 51, but you might read this slide and think maybe the next slide should be the conclusion. We have some target parameter that we're interested in. We just show that we can recover it from the data, and it looks pretty simple over here. We have recovered this from the data, but I don't think we're actually done. And I think perhaps it's unfortunate that we're not actually done. So here comes the not so good news. So if you think about applied work in the case where you have a multi-valued or a continuous treatment, if you think about, so what we did in the previous slide, we got you the average treatment effect on the treated, it's local to dose D. You have if you have a multi-valued or continuous treatment, you have lots of these Ds. And if I had these and knew what they were, if I were writing an applied paper, I think I would plot them. I would show a figure of here's the ATT of each dose, and it looks like this curve. It's going up, it's going down, whatever. The second thing I would want to do is compare them to each other. I would want to say if ATT of dose high is bigger than ATT of dose low, I would like to say that the causal effect of dose high is bigger than the causal effect of dose low. And this is going to be where the complications are going to come in. The other thing here is that if you're interested in average causal responses, so if you're interested in these derivatives, and these derivatives are what's going to show up in beta from the two-way fixed effects regression in a minute. So if you're interested in running that sort of regression, these sort of derivative terms inherently involve comparisons across different doses. So if you think about what's happening with a derivative, you're like taking ATT at one dose, looking at ATT at just a small increase in the dose and comparing those to each other. And so any issues that show up in comparing ATTs across dose, they're going to show up in derivative terms too. Okay, so let's see what happens. So if you have this, if you know what ATT that's local to a particular dose is, and you want to compare two different doses, let's see what happens. So I'm going to write these as DH. You can think of this as standing for a high dose relative to a low dose. These are things that standard parallel trends would identify both of these. I skipped maybe just one or two lines of algebra here, but this is just like add and subtract a couple of terms. And you can show that this difference is equal to, so this first term is a difference between potential outcomes under the high dose relative to potential outcomes under the low dose, specific to those who actually experience the high dose. Excuse me. And you can interpret this as a causal effect parameter. This is a difference between what outcomes would have been under one dose relative to another dose. This is a good thing. This is something we would like to recover. But you have this leftover thing that's the difference between, so this thing is, these are ATTs, so they're treatment effects. So you'll notice it has DL here and DL here. So this is at the same dose, but for groups that actually experience different doses. So it's like, what was the effect of the low dose? This is what was the effect of the low dose for the group that experienced the high dose, and this is relative to the effect of the low dose that the group that actually experienced the low dose had. These two things, parallel trends, difference and differences, it has nothing to say about this difference. It also, you'll notice this thing, so we could identify this term, but we don't identify this. This is a ATT it's about a dose, a counterfactual dose for the dose that experienced, for the group that experienced a high dose. And so standard difference and differences is not going to recover this. And this means that we can't recover or figure out what this selection bias term is. So Daniela asked me about if we're talking about a specific dose, if you need to discretize. I probably have been sometimes carelessly saying the word group that experiences a particular dose. If the treatment's actually continuous, there's not a group that experiences that particular dose. And I mean, I guess once you switch to like estimating this, if you may need to take like observations in a narrow range around a particular dose. But these arguments, the arguments, at least when everything's wrapped in kind of like population quantities, apply both with a multi-valued dose and with a continuous dose. Okay. And so I think I've kind of been saying this in words before I showed the slides here, but a key issue is going to be that standard parallel trends assumptions, they're not going to be strong enough to rule out these selection bias terms. So if you compare ATTs across different values of the dose, which I think shows up quite often in practice, you're going to get part of that. I mean, it could all be causal responses. It could all be selection bias. it could be a mixture of those two, and we don't really have a mechanism for figuring out what's going on. Okay, so in light of that, so the reason we were running into these issues is because the parameters that we were identifying were local average treatment effect on the treated type parameters. It suggested you might try to consider alternative parameters. And the thing that comes immediately to our minds, it probably comes immediately to your minds, is instead of going after ATT, to go after an ATE parameter, so an overall average treatment effect parameter. We can think about level effects and slope effects here. So the level effect is just the difference between potential outcomes under dose D relative to untreated potential outcomes. What's different here is it's not conditional on the particular dose being equal to D, but it's an average across the entire population. If you're interested in causal responses, you can take derivatives of this. This is in the case with a continuous treatment. If you have a discrete treatment, this is the discrete version of an average causal response. Again, you can think of all these things that are indexed by dose. They're tempting to think about, I mean, you might want to think about them as functions, but if you want an overall number, you can average them over the distribution of dose and get an overall number. This is sort of like corresponds to what's probably the natural target parameter, this overall average causal response, the natural target parameter for a two-way fixed effects regression. But you can think about whatever of these you're interested in. If you were able to recover these average treatment effect sort of parameters, you're not going to run into the same sort of issues in terms of making comparisons across dose. And to see this is easy. So if you're able to identify the average treatment effect of the high dose and the average treatment effect of the low dose, if you want to compare them, these are just this first term is the definition of the average treatment effect for the high dose. The second term is the definition of the average treatment effect of the low dose. If you want to compare them, you just see this YT0 cancels with this one. And so the difference between the two is just the difference between potential outcomes under the high dose relative to potential outcomes under the low dose. And so this is a causal response. It's an overall average causal response. And there's no selection bias term causing us trouble over here. It also means that these average causal responses, that if you want to take derivatives of these things, they're not going to be selection bias terms that show up there either. That being said, the key issue here is that even though these average treatment effect parameters are parameters that we like to identify, standard parallel trends doesn't identify these. It's not strong enough to identify these. And so what we're going to do is introduce new assumptions that are able to identify kind of overall average treatment effect parameters. We're going to call this strong parallel trends. And this is what it is. So strong parallel trends says that, so this is the difference between potential outcomes under dose D in the second time period relative to untreated potential outcomes in the first time period. So this is about a path of outcomes over time. And this is an overall average is equal to the difference between potential outcomes under dose D minus untreated potential outcomes, but specific to those that actually experience dose D. And again, like before, this is potentially helpful because we don't see this overall average path of outcomes under dose D, because we don't see YT of D for all units. We just see it for those who actually experience that dose, but we do see this path of outcomes. And if you're willing to invoke this sort of assumption, I'm going to come back and talk about why this is stronger in just a second, or why it's likely to be stronger. But if you're willing to invoke this kind of assumption, you're a few lines of algebra from showing that the overall average treatment effect at dose D is identified, and it's equal to this. This right-hand side is exactly the same as the expression for ATT was in the previous slide. It's the average change in outcomes among units, among those who experience dose D relative to the untreated group. In a second, if you hold on to the thought that this is exactly the same as for ATT a minute ago, there will be a reason why this matters. but the way we got here is different. So the assumptions are different, and the interpretation of the parameter is different than in the previous case. Okay, so let me make some comments about strong parallel trends. First of all, just at a high level, it's notably different from standard parallel trends. So one thing you'll notice, if I can go back a slide here, is strong parallel trends, it involves, it makes assumptions about all potential outcomes under each kind of dose. Standard parallel trends is an assumption only about paths of untreated potential outcomes. So they're kind of categorically different right off the bat, and in a way that makes strong parallel trends seem like it's likely to be maybe substantially stronger. Now, in the paper, we showed that strong parallel trends isn't strictly stronger. You can come up with cases where strong parallel trends would hold, but standard parallel trends wouldn't. But I think in practice, it's likely to be substantially stronger. I mean, we can come up with with a few cases where strong parallel trends might not imply standard parallel trends, but they're kind of few and maybe not realistic cases. But the other direction, we can come up with lots of cases where standard parallel trends would hold, but strong parallel trends wouldn't. Also, strong parallel trends, it's slightly weaker than this condition. So this condition is a form of treatment effect heterogeneity that the ATT, the local effect or the effect of the treatment that's of dose D specific to those who experience dose D, that this is equal to the overall average effect of dose D. Strong parallel trends it's not quite the same as assuming this, but it has this sort of treatment effect homogeneity sort of flavor. So another question in the chat is Yifan is saying, can you add an I subscript for the treatment effects? So these are average treatment effects that average across individuals. So that's why the I is gone on the treatment effect terms. Okay, and so just to wrap up this part about kind of the baseline case with 2 periods, is to start with, it's straightforward and the arguments are familiar if you want to try to identify ATT type parameters that are specific to those that actually experience that dose. And this is in the presence of a multi-valued or a continuous dose. But once you start to think about comparing these ATT parameters across different doses or to take derivatives of this ATT function, they start to include selection bias terms because they're local to specific doses. And what this suggests is trying to target parameters that aren't local to specific doses, like the ATE type parameters. But if you want to target those sort of parameters, it likely involves making substantially stronger assumptions than at least we have traditionally thought we were making when we said, at least when I say, I'm thinking about doing difference and differences. It would not be just be an assumption about paths of untreated potential outcomes. This would be, if anybody has a question, this would be a good time for a question. Otherwise, I'll jump into thinking about two-way fixed effects estimates.
We're gonna have a question, but it's probably poorly formed, so I apologize for that. But just thinking about this, when we have like a staggered setting, when we're thinking about sort of what that might mean or what we need for treatment assignment, in that like the treatment timing is as good as randomly assigned. Do we have something similar or analogous here? I mean, it's probably in that math that you had there, and I just didn't quite fully wrap my mind around it. But do we need something like that? The dose assignment is as good as I mean, that's kind of, I think that's kind of similar to the last one that you had there, in that it seems like that the dose or that the treatment effect is independent of the doses received. So I think that's kind of what's there, but I just wanted to clarify that for.
Yeah, I mean, so there are a whole bunch of trade-offs here. So like one of the nice things about going after ATT type parameters is you can allow for a lot of selection into the treatment. So if you have a binary treatment, you can allow for people who are going to experience good treated potential outcomes to select into the treatment on the basis of that. And now that sort of seems like a good thing because we think that people likely do select into the treatment based on their treated potential outcomes. But it may mean that the ATT is not equal to the ATE. And so this I think has the same sort of flavor that, like, if you target ATT, you're going to allow for a lot of selection into that amount of dose, but you're going to lose the ability to make comparisons across dose. And this would be sort of have the flavor of, like, if you had a binary treatment, if you know what the ATT is, it might be lots different from what the average treatment effect on the untreated would be. So I think that issue is going to show up here. I think what we're saying, I think strong parallel trends is not quite as strong as what you were saying, but it has the flavor of that. I mean, that would be, I think, a leading case where you could rationalize strong parallel trends.
So can I ask a question a little bit about diagnosing whether or not the strong parallel trends assumption would be reasonable? So like often you see people kind of say, you know, the X's are similar across these groups. And so that sort of maybe suggests that, you know, unobservable, you know, things like maybe the treatment effect size could be, you know, similar across groups. So this seems like one thing you could potentially do is kind of plot your dose received against some X's. And if that looks flat, maybe that sort of gives some faith to that assumption, or is that kind of a flawed reasoning?
To tell you the truth, I don't know the answer. So I might have to think about that more. This also, I don't know if Bacon is here or not, but he might be able to kind of better answer that sort of question than I am. Maybe the short answer is I don't know. Oh, go ahead, Bacon. Yeah, please.
Okay,
please
can you hear me? Sorry, I'm driving, but I have thought about that too. Like, if you can establish good balance in X across values of your dose, that could be part of an argument for, you know, strong parallel trends. I'm sure that there are lots of reasons it might need to go beyond that, but that has also struck me as a good first step towards supporting this type of assumption.
Sounds good. Thanks for the. I guess it's less like a question, more like a helpful comment. So thanks. Okay, I'll keep going. So the next thing we'll talk about here is two-way fixed effects. What two-way fixed effects regressions are going to deliver. I'm going to stay in this case with the baseline case, and we'll see what happens here. So here's the same two-way fixed effects regression, a slightly simplified version of the same two-way fixed effects regression that I showed before. Again, you have time fixed effect, individual fixed effect. Beta is going to be the parameter that a researcher would report from this. D is the amount of dose, and post is just a dummy variable for being in the second time period. In the case where you just have two time periods and no one's treated in the first time period, this simplifies this two-way fixed effects regression. Simplifies into just a simple linear regression of the change in outcomes on the amount of the dose. And I think typically researchers interpret this beta parameter as, at least hopefully, some kind of causal response or average over heterogeneous causal responses. So what we show in the paper is that this beta two-way fixed effects, under standard parallel trends, what it corresponds to is, maybe this looks complicated, but all this is a weighted average. So here these W's are weights. This thing is this local average causal response term. So it's the effect of a marginal increase in the dose among those that are experiencing dose L, and you're averaging over L. This thing corresponds to the selection bias term. So, and it's going to be the trouble here. And this last thing, you don't have to worry about this too much. We think about a setup where the dose looks like, so there's a group that experiences no dose, and then the dose is continuous over some range. So I don't know, 10 to 20, or from some low dose to some high dose. And some of the weight from beta two-way fixed effects is going on to the effect of going from no dose to the smallest possible dose, and that's this term. But the important part is that under standard parallel trends, that this weighted average, it includes both causal responses and selection bias terms. And so in some ways, beta is confounded or polluted by these selection bias terms if all you invoke is parallel trends. I'm going to come back to provide some more details about the weights in just a second. But for the moment, let me just say that the weights are all positive and that they integrate to 1. So there are no negative weights here. I'm going to try to argue, to me, positive weights is a very minimal requirement on something being a reasonable weighted average. I'll show you a couple of pictures about that in just a moment. But at least there are no negative weights here, which is sort of a good thing. I think the main trouble is this selection bias term. If you're willing to invoke strong parallel trends, beta is equal. This is the same weighted average, but strong parallel trends is able to kill off the selection bias terms. So you get a weighted average of overall average causal responses. And so just to kind of interpret what this means, so I think the primary issue number 1 here, is that if all you invoke is standard parallel trends, selection bias terms are going to make beta from a two-way fixed effects regression hard to interpret. Besides that, the second issue is about the weights. They're all positive, but again, they're driven by the estimation method. And strictly in all positive weights, I think I said this before, is one requirement for reasonable weights, but it's a very minimal requirement. You can still have strange weights that are all positive. One of the strange properties of these weights is that they're maximized at the expected value of the dose. This can lead to some weird things. I'll show you this in the next picture here. So this is an extreme case. So the left-hand side is density of a dose. This is just made up. But if your dose followed this is a mixture of normals, this bimodal distribution. If your dose followed this, I mean, I don't think many doses follow this distribution, but just to illustrate that you could get weird weights. What the weights from two-way fixed effects regression on beta, what they would do is they put the most weight here in the middle. You'll notice in the middle, so the middle is about 8. There are very few units that actually experience dose 8, but two-way fixed effects puts a lot of weight on those units. If you look around 4 or 12, you can see a lot of units are experiencing doses like that. But in the two-way fixed effects regression, those doses are not getting very much weight. So this would mean if you were in the case, so say here, if you have heterogeneous effects of dose, so say the effect of dose, the marginal effect of dose was small around dose equal to 4, it was big around dose equal to 8, and it was small again around dose equal to 12. So it's small, it increases, and then it levels off. You could get kind of poor estimates if you use two-way fixed effects, because there are very few who'd be experiencing the big effects in the middle, but two-way fixed effects would be putting a lot of weight on those heterogeneous effects. Another kind of similar picture, maybe with a less crazy distribution of the dose, is if the dose follows an exponential distribution. Here, this is an exponential distribution where the mean is 1. This is a skewed distribution. So the mean is 1, but you see a lot of observations that are having doses, I don't know, around 0.4, 0.6, or 0.2 or something. And then you occasionally get a dose that's much bigger. Two-way fixed effects, so it puts the largest weight on the average dose, which is here when the dose is equal to 1, but it still also puts a significant weight on, say, marginal effects of the dose when the dose is equal to 4, even though almost no one's experiencing doses being equal to 4. So in a minute, I'll argue that I think you can do better than two-way fixed effects by, let me go back one side, by basically weighting according to the actual density of the dose, rather than just picking up the weights that come from two-way fixed effects. The last issue Akash, I see your hand. Let me go one more slide here and then I'll come back to you. The last issue here, and this is kind of shoehorned into this place, is that remember that the expressions for ATE under strong parallel trends and the expressions for ATT under standard parallel trends, they were the same. So I think researchers, including me, are very used to the idea of exploiting pre-treatment time periods to think about whether parallel trends assumptions actually hold. So like do something like pre-testing. But because these expressions for ATE and ATT are the same, the information in pre-treatment periods is the same. So if you want to look at what's happening in pre-treatment periods, if you would reject standard parallel trends, you would also reject strong parallel trends. If you would not reject standard parallel trends, you'd also not reject strong parallel trends. So there's not a channel for like going back in the past and trying to pick up if one of these is more if strong parallel trends is valid. Is there a question, Akash? I think this would be a good time for a question.
Okay, cool. So it was based on your the graphical representation that you had in the earlier case. So I was just thinking, this just made me think about if weights can be adjusted to have like a sort of a kernel of a triangular weighting system where you give the weights a lot to the folks at the center and then it just goes to 0. Or you could even have it like Stepanechikov sort of a way. Have you thought about, can that be incorporated, or is that a very
what was the last thing you said?
So like what we did in like RDD, you would have like a triangular weight or a EPAN weight or a rather than a uniform weight. So I was thinking, would that complicate stuff, or is that very deeply? Yeah.
Well, it would complicate stuff in the sense that if you want to do that, and this is what we would suggest to do, something like what you're saying. If you want to do that, then you just shouldn't use two-way fixed effects. You should do. I mean, I would suggest kind of sort of like a non-parametric regression of changes in outcomes over time over the dose. And I think that's along the lines of what you're saying. But remember, so like in practice, like we observe the dose, so we can pick up what the distribution of the dose is. And at the cost of just more complicated estimators, we can weight things by this dose instead of this one. And this is, I think, kind of a general purpose strategy, is pick the weights that you want. And the natural weights are the weights that come from the distribution of the dose, rather than using the weights that two-way fixed effects assigns you. So I hope that answers your question. Melanie has a question about event studies. Yeah, I mean, I think you would definitely want to see no pre-trends, but the thing I'm saying here on this issue number 3 is no pre-trends by itself isn't enough to tell you whether strong parallel trends holds or only standard parallel trends. That's just not enough information to distinguish between the types of assumptions we're talking about here. But if you see violations of parallel trends in pre-treatment periods, I mean, that would be bad in either case. Okay. And then, so this sort of segues into what should you do? So faced with the issues that we're pointing out, what should you do? So one option is just report average ATT parameters as a function of the dose, just report them directly, but interpret them carefully. So we can recover what's the average treatment effect for people of a low dose, for people who experience the low dose. We can get that. We can also get what the average treatment effect is for people who experience a high dose, what the average treatment effect of a high dose is for people who actually experience a high dose. We get that too. But you should be very careful about the comparison between the two. So you could stop there and just report those local ATTs, and that works under standard parallel trends, but the comparison is the tricky part. The second thing is at least be aware or think through that if you want to return beta from a two-way fixed effects regression, or if you want to make comparisons of treatment effects across dose, or if you want to go directly to kind of an average causal response parameter, all of those things are going to require stronger assumptions than just standard parallel trends. So you should at least be aware of that, at least kind of caveat your results, at least kind of realize that one explanation for differences in effects across dose is causal effects. Another explanation is inherent differences among those that experience one dose relative to another dose. And then this was the question from a second ago, but with regards to the weights, I think in general you can do better than the weights that, even if you're willing to invoke stronger assumptions, I think you can do better than the weights that two-way fixed effects gives you. I think the way that you could do this is doing kind of first step non-parametric regression. This would be an easy sort of non-parametric regression because it's just a regression on one variable. So there's no kind of curse of dimensionality here. When our code eventually comes out, this will be the kind of strategy that we follow. If you want to get it into an overall number, you can weight by this term would weight these heterogeneous causal effects by the actual distribution of the dose instead of by the two-way fixed effects weights. And I think that this approach would almost dominate two-way fixed effects, with the exception that it's maybe a little bit more challenging to implement rather than just running a fixed effects regression. But that being said, even if you do this, it doesn't get you around the issue related to standard parallel trends versus strong parallel trends. Okay, so in the remaining few minutes, I'll talk about the more general case with multiple periods and with variation in treatment timing. A lot of the arguments we've already talked about we're going to go through in this case. So I think if you feel good about what we've done so far, then this part will be kind of an extension along the lines of what other papers have already done in the binary treatment case. So first, let me just kind of set the stage. We'll be thinking about staggered treatment adoption with a continuous or multi-valued treatment. So in other words, if you're treated today, you continue to be treated and with the same dose in the future. We're going to show some complications in this case. If you make the setup more complicated, I don't think it's going to make things better. It has the potential to make things worse. We can, some of the issues in the literature like treatment effect and anticipation, we could allow for those things too, but we're just going to ignore to keep things simple. Oh, and here, once you become treated, the dose remains constant. And then just a little bit of extra notation here. So I'll introduce this variable G, which is going to indicate a unit's, what I'll call their group or their timing group, which is a time period when an individual or unit becomes treated. So if there are 10 periods of data, you become treated in the 5th period, you're in group 5. We'll also have potential outcomes. They're slightly more complicated here. So this is a potential outcome for individual I in time period T. This is if they were in group G and if they experienced dose D. So this allows you to think about like what would happen if you were assigned a different group. So if you became treated at a different point in time, or if an individual experienced a different amount of the dose. And then again, I'll use a notation YT0 for the outcome that individual I would experience if they were untreated in all periods, if they were never treated. Okay, and here, so we can think about the same sorts of parameters of interest. The notation is getting a little bit heavier here, but it's very similar in spirit to what we talked about before. So you can think about level effects, so treatment effect on the treated type parameters. So now they're indexed by group and by time period. These look like, if you remember my paper with Pedro, where we talk a lot about group time average treatment effects, this is like a group time dose average treatment effect. And it's local to a particular group, and it's local to a particular amount of the dose. And you can see that, maybe I won't drill down into this, but it's what you'd expect. It's the average treatment effect of the potential outcome corresponding to that group, that dose relative to not ever being treated, and it's local to that group and local to that dose. You can also think about average treatment effects that are not specific to, not local to a group or not local to a specific amount of dose. So you see these things don't condition on group or dose out here. Like before, we can think about slope effects. We can think about derivatives of these things. So this is average causal response on the treated. Now it depends on group, time, and dose. This is an overall average causal, an average causal response that comes from taking the derivative of this ATE parameter. Again, it depends on group, time, and dose. If you had a discrete dose, you could think about discrete versions of these. If you want to average them in other ways, you can do that. Let me mention a couple of those next. Continuing to think about parameters of interest. So like before, these ATT or ATE parameters, they essentially inherit all the same issues as in the 2-period case. So ATT parameters are going to be identified under a multi-period version of standard parallel trends, but they're going to be hard to compare to each other. ATE type parameters, they're going to be easy to compare to each other, but they're going to require a multi-period version of strong parallel trends. This means under standard parallel trends, if you want to make comparisons, or if you want to think about these causal response terms, or in a minute, if you want to think about beta two-way fixed effects, they're going to contain selection bias terms. And then the rest of the slide is what I said before I showed the rest of the slide. Okay, and then so one of the issues here is that, especially when you go to group, time, dose sort of parameters, these are high dimensional. They'd be hard to plot, they'd be hard to understand if you're able to recover them. And one idea would be to aggregate them. So somehow average across group, average across time, average across dose into some higher level parameter that you might be interested in. I'll give you a few ideas here. So one idea would be to average across, so average by group across all their post-treatment time periods, and then average across groups. This would get rid of the group and time indexes in the parameters, and will give you kind of an overall. So here overall means across group and times, but will give you an average causal response as a function of dose. You could plot this, it would be a 2-dimensional plot that would be pretty easy to interpret again. Another idea, if you want just one number, so like beta two-way fixed effects gives you one number. If you want to summarize everything in one number, you can average again this thing over the distribution of the dose and get an overall average causal response. This is kind of the natural target parameter for a two-way fixed effects regression. We'll see that two-way fixed effects isn't going to be equal to this in general, but it's the natural target parameter here. Alternatively, I think there have been a few comments about event studies. You can pick weights and average in particular ways. We talk about this in the paper, ways you can do this, where you can get the average causal response of a particular dose at different lengths of exposure to the treatment. If you average those over the dose, you can get kind of an overall average causal response at different lengths of exposure. I think this would correspond to the interpretation that people most often give if they run one of these event studies sort of regressions, but have a continuous treatment. I think that's the flavor, the way that these are commonly interpreted. But you can recover any of these. And then to finish up here, I'll quickly talk about what happens to two-way fixed effects, in this case with multi-valued or continuous dose, but you have staggered treatment adoption. So here's the same regression as before. Just to remind you, so D is the amount of dose, and treat is a binary variable for whether or not you're treated in the, or an individual or unit is treated in time period T. Here, so I'm going to show some expressions that look complicated, and then I'll bring it back to some pictures that Bacon made. You can probably tell that Bacon made these pictures, but that I think of kind of just a simple running example that I think can kind of explain some of the terms. Here, what there is, just to explain this picture, is there are two timing groups. There's an early treated group called group G, a late treated group called group K. These periods pre-G are pre-treatment periods. These are the periods before group G becomes treated. So no one's treated yet in these time periods. These periods labeled mid, they're the middle periods. They're after group G has become treated, but before group K has become treated. And the post periods are after both groups excuse me, after both groups have become treated. And within each group here, there's variation in the amount of dose. So within the early treated group, there's a low dose group. I think it's this line, the solid black line, but there's a low dose group and there's a high dose group. So the low dose group experiences dose equal to 2. So it's a multi-value treatment here, multi-value discrete treatment. The high dose group experiences dose equal to 4. Same for the later treated group. There's a low dose group there, but it's a dose is equal to 5, and a high dose group with dose equal to 6. And we'll zoom in on the sorts of comparisons that show up in two-way fixed effects. Okay, so in the paper we showed that beta two-way fixed effects is going to be a weighted average of 4 different terms. The first term is this one. You don't necessarily have to understand this, but the intuition is that it comes from within group, so within a timing group, so like for group G or group K, variation in the amount of the dose. And this term is very similar. This is like looks like a simple linear regression of changes in outcomes over time on the amount of the dose. So it's very similar to the baseline case that we showed earlier, where there are 2 periods and where there were exactly 2 periods. Under parallel trends assumptions, this corresponds to a reasonable treatment effect parameter. So you can turn this into something that's a derivative after some manipulations that looks like a derivative or looks like an average causal response. Those arguments look like the ones I showed you in the baseline case before. But under strong parallel trends, it corresponds to an average causal response parameter, which is a reasonable causal response parameter. Under standard parallel trends, it's going to include both the causal response and a selection bias term. So these 4 terms that I'm going to show you, where this one is the first one, 2 of these are going to show up in the case of the binary treatment, 2 are not. 2 are going to be reasonable, 2 are not going to be reasonable. This one is both, at least under strong parallel trends, it's both reasonable, but it doesn't show up in the case. It doesn't show up in the case with the binary treatment, because in the case with the binary treatment, within group, there's no variation in the dose. The dose is all the same. So this term isn't there. And if you go back to the picture, so this term corresponds to, so this is the early treated group. This is the group with the low dose. This is the group with the high dose. Here, the group with the high dose, their outcomes, they jump when they get their higher dose. The less treated group, their outcomes also jump, but they don't jump by as much as the higher group. So this difference from from these periods to the early periods and these periods to the early periods, this shows up as part of where beta from the two-way fixed effects regression comes from. The same thing happens for the late treated group. So the high dose group jumps more when they become treated relative to the low dose group, and comparisons pre versus post, post relative to pre for both groups, they show up in the beta two-way fixed effects. The second term, so remember group K is treated after group G. It comes from comparing paths of outcomes for a group that becomes treated relative to a group that's not yet treated. So this is paths of outcomes for group G relative to group K. All these in middle and pre-periods, these are all untreated potential outcomes for group K. So this sort of thing, it's a reasonable treatment effect parameter because it's a group that's treatment is turning on relative to a group that's not yet treated. So those are the sorts of comparisons that we want to show up. Under strong parallel trends, this corresponds to average causal response parameters. Under standard parallel trends, it's causal response parameters with selection bias. So that issue is still there. And let's see, do I want to say anything else here? So this is in the category of reasonable treatment effect parameter. And this is also the sort of term that shows up in the case of the binary treatment, that you're comparing a group that turns on to a group that hasn't turned on yet. In the picture, so here the dotted line is group K, and their treatment doesn't turn on, so they're just trending along. They're not affected by the treatment yet. And part of beta comes from this jump in outcomes experienced by group G, which is the group that becomes treated here. We like for that to show up to affect our estimates of the effect of participating in treatment. Oh, now this looks very nasty. The next thing is this thing. Let me delete that mess there. What this is a term that comes from comparing paths of outcomes for a group that already becomes treated to, this is a typo here, paths of outcomes for a group that already becomes treated, so that's group K, relative to paths of outcomes of an already treated group. And that shouldn't be group K, that should be group G, so the already treated group. And this is a term that in the presence of treatment effect dynamics, it corresponds to a reasonable treatment effect parameter. So paths of outcomes for group K relative to paths of outcomes for units that never become treated. But these other, that stuff that I just deleted are treatment effect dynamics terms for group G. You see they come in here, they don't disappear. This is where you could get negative weights from, and we don't like that this stuff shows up in the treatment effect estimate. So this is a term, so in the binary treatment case, this sort of term is the problematic term. If the treatment were binary, it continues to be problematic in this case. And here in the picture, this is how outcomes change for the group that becomes treated, late treated, but it uses the comparison group as the already treated group. Here, it doesn't look like they're treatment effect dynamics, so things might work out okay in this case. But if treatment caused this group to, when they become treated, like for their outcomes to zoom up to the top of the screen, then things could go haywire. And then the last term is, and this is a term that doesn't show up in the case with the binary treatment. It comes from comparisons for groups G and K, so groups that vary in their treatment timing in their common post-treatment time periods relative to their common pre-treatment time periods. And it shows up in the case where the average amount of the dose is different between groups. And so it's a comparison where, I think this is actually mislabeled maybe, but it's a comparison of how much outcomes jump for, so this should be, the dotted line should be group K. On average, their dose is higher than for group G. This is the part that's mislabeled. But how much outcomes jump post relative to pre for the higher treated group relative to the group that has a lower dose on average. This term, I'll skip the details here, but this term can include problematic terms that can deliver negative weights again for the two-way fixed effects regression. And so just to summarize here what the issues were, if you're in the case with a two-way fixed effects regression with multiple periods with variation in treatment timing and with treatment effect heterogeneity. So to me, the primary issue is still these selection bias terms that show up if you invoke standard parallel trends, the sort of parallel trends assumptions that people probably think that they're using. And it complicates interpreting beta two-way fixed effects. Second, the weights are, they suffer from all the same issues as in the two-period case, but they also have these additional issues that come through treatment effect dynamics and through heterogeneous causal effects that can lead to negative weights. And this means that if you, for the same reasons that you might feel uncomfortable with using two-way fixed effects if you have a binary treatment, you should continue to feel at least as uncomfortable, even if you're willing to invoke strong parallel trends. The weights issue, it can be solved by carefully making the comparisons that you want to make. But the first issue, the selection bias term, it's a more fundamental mental challenge, involves making stronger assumptions. That's all. I guess I've taken this to the time limit. If people want to stick around and chat, I'm happy to do that. At the tail end of this last slide, I just have a link to the paper. We have a couple of kind of less technical summaries in a couple of papers. And certainly, if you don't want to stick around for a minute, I'm more than happy to talk via email. Thank you.
Thanks very much, Brant. I think there are a couple questions popping up in the chat.
Yeah, okay, so let me see. I got behind for a second here. Yeah, so the first question to Yifan is, so conditioning on G, it just means conditioning on a particular group that's defined by their timing. It still allows for different individuals to have different timing. So I don't think this is too much of an issue.
Yeah,
About, yeah,
but
sorry, go ahead.
yeah, I'm sorry. Sometimes, like, I can see from your slides with the subscript, like, for example, even for YT parenthesis GD, like, I still feel like it doesn't matter if we add a GT, if we add the YT, like a I for the
Yeah, here.
Yeah. So when we like write an expression for ATT or ATE here, like I mean, in the expression, I didn't see with the subscript I, but here we have a subscript, so it doesn't matter, right? Since
Yeah, it doesn't matter. So this is just the notation that I'm used to, is to drop the I subscript here. I mean, so this is not an average treatment. It's not a treatment effect that's specific to unit I, but it's averaging over like all units that are in this particular group and that have this particular dose.
Okay.
Some people might put it. I don't usually put an I here, but other people have different notations where you could put an I there.
Okay, thank you.
And then move it. Let's see. Daniela has a question here. So the question's about time invariant covariates and whether that could affect whether the selection bias issues and strong parallel trends. I think the answer to that is potentially it could be more plausible if you condition on some covariates, but my guess is that you're just kind of like, at least conceptually, you're kind of pushing the ball down the field a little bit, if that makes sense. That maybe strong parallel trends would be more plausible if you condition on X, but you still would have a hard time, I think, distinguishing between standard parallel trends conditional on X and strong parallel trends conditional on X.
Awesome. So I have a couple questions. One, I think it's super cool that by splitting up this into the doses, we can actually do something that we couldn't do with the binary treatment case, which is look at kind of the dynamics after everyone has received their treatment, because in a binary case, you can't do that, right? But now we can. So if you were in a situation previously where you were collapsing your treatment to something that was binary so that you could get an estimate, now you don't have to do that, and you get a lot more valuable information afterwards too. So I thought that was just really cool. And
yeah, Taylor, thanks for saying that. I really did not emphasize that at all, but maybe if I can quickly find this in the slides. If you think about, if you're interested in causal responses, here, if you think about this sort of term, if you're thinking about causal responses, so if you want to take a derivative of this, when you think about how ATT changes when you change a dose, this second term isn't changing at all. So you no longer have to see a group that experiences no dose. So this is, and I probably should have emphasized that way more. They're like, it is a cool thing that if you have multiple values of the dose, that you can use that under parallel trends assumptions to recover treatment effect parameters that you'd be interested in. So yeah, I'm glad that you said that.
Yeah, I think that's probably one of the coolest parts, and it goes in the good news column, which is always nice.
Yeah, that's right. I probably, the next time I do this, I should probably have a good news side, a bad news side, and a good news side.
One of the things I had a question about was kind of in a case where you do have this continuous treatment, and you had that term that was kind of, I guess you might call it the extensive margin term. But do you think that you might actually have something that corresponds more closely to the average treatment effect on the untreated for those they're kind of marginal compliers at the treatment. If you think about them as selecting into treatment, do you think there's more useful information there, or something that they might be able to exploit to maybe some suggestive evidence perhaps of the ATE?
I don't know the answer, Taylor. I just don't know.
It's a pretty strange question, I think.
Well, I mean, I think that there's like so like they're kind of interesting things. Like if you think about like these selection bias sort of terms, I mean, you could write down a model. So like if you live in a world where maybe everybody, like you fully control what dose you go into and you optimally select your dose, then that starts to look like something where all these causal response parameters should be negative, 0 or negative. Like you chose the best one for you, and so if you move to something else,
envelope theorem stuff.
they're just going to make your outcomes worse. And so that maybe says something. Maybe that suggests that a lot of like what you're getting is actually selection bias instead of causal responses. But under different scenarios, I mean, you can imagine different things. I think like I kind of grew up in graduate school thinking about partial identification. I mean, I think there's kind of a sense that like there might be kind of nice assumptions that you could make that are in between strong parallel trends and standard parallel trends, where you could still learn some things, but maybe you're not quite as strong. I mean, I sort of guess that maybe those start to become more application specific, but I think that's an interesting route to try to proceed.
I think Dan Miller will be very happy to hear you talking about the applications of potential identification in this context.
Yeah.
I think my last question, if that's cool, is about, say that you had a setting specific reason to believe that the dose would drop off after a certain period of time. Could you just like do your weighting in like an event study situation for relative time and then drop the periods after you think that the dose would no longer be constant? Or is there contamination for those extra periods that you're dropping? Like are the estimates taking on some of those the height?
So which is dropping, you mean you go from like some dose to not being?
Oh, sorry, Brant, I think that you're breaking up there.
Any more sense?
Yeah.
Okay, well, I'll try to answer Taylor's question. Is I don't think that things are going to get easier in that. I don't think that things are going to get better for two-way fixed effects regression in that case. But I do think that, at least from an identification standpoint, I mean, you can just kind of keep track of this. So like, I mean, if dose is changing over time, or if people are moving into and out of treatment, you can define groups. Like I was writing ATT or ATE of group, time, and dose. If you need to keep track of more things there, you could keep track of more things there. And I think from an identification standpoint, it would work. I think there may be practical issues, kind of cursive dimensionality issues, where it's not clear if you actually have sufficient data to recover treatment effect parameters there. But I think identification-wise, I think it's fine.
Sorry about that. I guess I dropped out there.
Well, so I still attempted to answer your question. I think maybe if we want to talk more after, I'd be happy to do that.
Perfect.
Sorry, a couple more questions here. Taylor, do you think we should, I know I'm after the time. Do you think we should like just have people who want to stick around for a few minutes, stick around and not hold people who want to?
Yeah, we can do that. Sometimes I like to have the questions recorded because people who are watching might have similar questions.
Oh yeah,
Like
I'm happy to keep. Yeah, I'm happy to keep the recording. I just didn't want to hold people who were being polite to stay
Oh
on.
yeah, absolutely. So if you want to leave, then you feel free to. The recording of this will be uploaded. And again, just then before everyone who has to leaves, I just want to thank Brant again for being so generous with his time and presenting this work. So thank you very much, Brant.
Oh, thank you for having me. Okay, I'll try. So I got a couple questions in the chat, Taylor. So one is from Raleigh. Yeah, so Raleigh, I think your question is similar to Taylor's. I think so. Like, if the dose varies over time. Okay, so all our results are quite negative for two-way fixed effects regressions in this case. And I don't think two-way fixed effects regressions, if you make things more complicated, I don't think those are getting better. But if you think about identifying sort of average treatment effect parameters, I think you should be able to write down identification arguments that are very similar to what we've had. So I defined like group, time, dose, average treatment effects. But if you wanted to define more complicated parameters in that, if you wanted to index them by like if people can move in and out of treatment, then the groups would become more complicated. So you could have a group that becomes treated, then leaves treatment for a while, then becomes treated again. That's not really an issue. If you want to let dose vary along with that, that's not really an issue. But those are, when I say those are not an issue, I mean from an identification standpoint, I can write down ATT of really complicated thing equals follow that path relative to the group that's never treated, and that's going to work. But if you take that to data, then that's going to be a different ball game, because if you try to estimate that, you're going to have to find observations that follow that path of moving into and out of treatment with different doses and things like that. And that starts to look like a curse of dimensionality that you're going to have a lot of observations in order to be able to find a few that experience very complicated treatment regimes. So I think that that's kind of maybe less of an econometrics issue and more of a practical issue, but is probably likely to be a hard issue to deal with in most applications. The question from Daniela is about how we should create low and high dose groups. I don't think you actually have to do this. So maybe my kind of constant referring to high dose and low dose was perhaps confusing. You don't have to break things into high dose and low dose. You can keep everything continuous and just work with the actual doses that people experienced. High dose and low, if you have a discrete high dose and low dose, that's kind of like the simplest case where what we're talking about applies, but it certainly continues to apply if you have a continuous dose. And so in my view, like I think there's often kind of like a strategy of like a practical strategy of if you have continuous things, continuous doses, continuous covariates or something, sometimes it may be convenient to make those discrete. Sort of in my view, we ought to treat continuous things as actually being continuous. And I think that applies here. Thanks, Danielle.
Brantly, can I ask you one other question?
Please.
Yeah, so I'm trying to think about, so where I get from all of this is, you know, there's not an easy solution. We have to think about whether we believe stronger assumptions. Perhaps during this conversation, people have had some ideas about maybe if there's balance on X's across dose, maybe that's some good signal that this is going to work. But obviously, we don't have a clear test. So at some level, what I see as when I'm going to be a referee, or if I'm an editor on a paper, or if I'm writing a paper like this, I need to be able to explicitly state out what the assumptions that are underlying, what you should believe and what you shouldn't. And what I sort of understand is, hey, if I'm going to claim that this is causal, then I have to convince you, or we all have to accept that the effect, how much dose you have, the parallel trends assumption sort of holds across dose. Like if a high dose person had been instead given a low dose, they would have had the average treatment on the treated as the low dose person that got the low dose. And similarly, if the low dose person had gotten the high dose, they would have had the average treatment on the treated as the high person who got the high dose, right? Essentially.
Yes, I think
Okay.
that's right.
Okay, so great. So at least I didn't totally miss what was going on in the conversation. But so where I'm trying to push is, are there ways in which I could say, what if I have intuition that I think the high dose people are the ones who knew that they could get the most out of it? And so my belief is that I have a directionality of it, which is if I gave the high dose person a low dose, their treatment effect would have been bigger than the low dose people who got the low dose. Or similarly, if a low dose person got a high dose, they wouldn't have gotten as big of a treatment effect as the high people who actually got the high dose.
Yeah.
Which I think, if it's a positive treatment, obviously you can switch these all the ways. But let's say I think that that's the most reasonable. Am I able to then say something about the direction of the bias?
So I mean, I think this is very much has a flavor of like kind of a partial identification sort of argument, that if you believe some kind of sign restriction or something like that.
Yeah.
My guess is what would happen is that you would get. So I can't think all the way through this, but my guess is that like what you would get is something like that. The effect is probably either greater than or less than whatever you actually recover at different values.
Okay.
Of the dose. And I think we're often kind of like used to those sort of arguments. Like if you can come up with a lower bound, then you may not get exactly the thing that you're interested in. But if you see that the lower bound is positive, that's pretty informative.
Yeah.
So I mean,
cool.
We don't necessarily have all those things worked out, but I think those are very interesting sort of directions for like how to like if you just feel like I can't bite off this strong parallel trends assumption, but I still want to learn something, I think these kind of like partial identification ideas are kind of the immediate thing that sort of pops into my head is ways that you might be able to at least in some cases be able to like sign the effect or
so
something
perhaps
like
my humble suggestion would be, to the extent that those of you who are working incredibly diligently on this topic can provide some of that, those sort of partial identification ideas, understanding that you can never know if those other assumptions you're placing on that partial identification are right or not. But having those built into our framework of thinking about this, I think would be helpful, because like you say, the strong parallel trends assumption is going to be a lot for any of us to bite off. But I think what we'd like to be able to put in our papers is, let me give you a sense of what I think the direction of the bias is likely to be. And then the reader can decide whether they believe that story you're telling or not, versus, hey, do you believe strong parallel trends? No, I don't. And so now I don't have anything, right? So
thank you. That's a very helpful comment.
Alrighty. But if there are no more questions, I think we'll let Brant go. He's been very, very generous with his time. Thanks for all the great questions, everyone, and for the great turnout. So have a great weekend.
Thanks so much. Thanks a lot.
Okay, thanks, Taylor. Bye-bye.